Hello everyone and welcome back to the channel. So today we're going to be going over the 5 main steps in helping your model learn or even train faster and more accurately. So if you're ready, let's begin. So have you ever tried to train a neural network and see that it just refuses to learn, or it's giving a lot of mistakes, it's not training properly, or it's just memorizing and not actually learning? So this can be seen by the accuracy, it's low, or the accuracy doesn't change when you train it. No matter how many times you train it, it just stays the same or it even gets worse. And this is actually one of the most common problems beginners run into when they are learning machine learning. And however, the good news is that in most cases, it's not actually a complicated problem, and it usually just comes down to small and usually fixed steps that you can take to manage this issue. So that's what we're going to be looking at today. I'm going to show the 5 main common reasons and how we can fix those problems in very simple steps. And this will be a practical video, so we'll easily be able to do it through our code that I'll show. So we will start with a model that performs quite badly, and then step by step we'll fix each of the problems by identifying them and then solving them, so you can watch the accuracy improve in real time. And everything will be done using Python, the PyTorch module which we'll be using, so you can follow along easily. So now we can head over to our IDE and I'll see you guys there. So here's the baseline starting model that we're going to use. So it's using the MNIST dataset. So basically it just contains the handwritten digits from 0 to 9, which we did similarly before. And each image, it contains 28 by 28 pixels. And this model will just try to predict which digit it sees. So just a quick recap of the entire model. So here we first load the dataset, then we split it into training and test data. Then we define the neural network, which will take one input layer and one hidden layer, and at the end one output layer. And for the output layer we defined 10 neurons, as you can see here, 4 and 10. So one for each digit, from 0 to 9. And then we define a loss function and the optimizer, like usual, which control how the model will do the learning. And finally, there's the training loop down here. And this training loop will just run over the data, and the test accuracy function, it will just run that each time to show the accuracy. So this looks pretty reasonable at first glance, but there are actually some problems hiding in there that make the model perform worse when it's actually learning. So even if we run it, let's see what we get. So using the device, your CPU, as you can see, it gives a 64%. And so for a dataset, especially like the MNIST dataset, it should realistically be higher than 90 because it's a really easy dataset to work with. So actually 60 or 70 is not a good indicator. And there are a few ways to actually fix this. So let's go ahead. So the first one which we did was fix the learning rate, right? So here we can see in the optimizer, the learning rate is equal to 8. So, and the learning rate, it controls how big the weight updates are during the training. So right now, since it's 8, which is extremely aggressive number, because the optimizer is taking the massive steps and basically jumping all over the place instead of slowly improving. So a good learning rate is actually a lower learning rate, but not too low. So an optimal one is somewhere between 0.01 to 0.1. So if we change it to 0.01, and this will definitely help it learn better. and we'll test it at the end as well. And yes, so the next one is the fact that the network is too small. And by the network, we mean the amount of neurons we put. So if we go up here, over here at nn.linear. So our hidden layer has only 4 neurons, as you can see here. And that means the model is trying to understand the thousands of the handwritings just using 4 values. So we actually need to increase the model capacity so that it can actually learn the patterns from the data. So we can do this just by increasing the number. So if we go here, the code, we can say instead of 4, we can put 128 and 64. And we can even increase the FC1, put 128 here. And yes, that should be it. So when we change this, we also have to update the forward function we have. So go over to the forward. So you can see here x.view minus 128 by 28. And we need to add a second line. And actually, before we add the second line, we also need to add one more layer. So just we do copy this, self.fc2, we do self.fc3. And we can set it to, let's say, 64 and 10, just for now. So now if we go to the forward function, we add the extra layer we did. So fc2.x, and for the final one, fc3.x. So now the network goes from 784 inputs to 128 neurons and 64 neurons. Then we give it finally 10 outputs. So we can see that it has much more capacity to learn. And for the third fix, it's the activation function. So if you see here in the just above the forward function, we have self.activation and n.sigmoid. So since we're using sigmoid, this squashes the values between 0 and 1. And the issue with the sigmoid is that when the values are very small or very large, the gradients will just basically disappear. And this is called the vanishing gradient problem, which will make the training slow and inefficient. And a simple fix for this is just to switch to another activation function. So there's a couple, and we can just use, for example, ReLU, which stands for rectified linear unit. And this function is much more efficient and usually a recommended choice in most modern neural networks. So that's why we also use this one here. All we do is nn, nn.relu. So as you can see, it's just a simple one-word change, and this will help the gradient flow properly during the training, and which will allow the model to learn faster and more reliably. So the fourth step that we took is the batch size. So we need to fix the batch size, because the batch size, it controls how many images the model looks at before updating its weights. So if we go over in our code, find the batch size over here, train loader. So with a batch size of 512, the model is averaging over a very large group before making any updates. So it makes the gradients pretty much very noisy, and overall the learning becomes less precise. So a normal batch size for MNIST is 64, because the smaller the batch size is, the more frequent updates and usually better learning it gives back. So we can just go ahead and change to 64. So good. And so yeah, after more frequent weight updates, the model will learn more efficiently from the data. And the final fix we can apply is fixing the number of epochs, so number of times the loop runs. So right now you can see it's epoch equal 2. So basically an epoch is one full iteration throughout the entire training dataset. So for example, if we have here 2, it means that the model iterates over the dataset twice. And just 2 epochs means that the model barely has any time to learn anything. So we need to increase it so that it can go over the training dataset much more and get more used to it and have proper time to train on the dataset. And this will improve the accuracy as well. And not by accuracy, the learning process as well. So a good number or a standard number is 10, for example, here. It can be any number depending on the size of the dataset, of course. So, of course, also when we have 10 epochs, the training will take a little longer, but the learning will keep on getting better and faster with each epoch. So now that we have applied the 5 changes here, we can go ahead and now test the accuracy and the learning. Let's wait for it to load up. As you can see here, for the first step, it became 81.85, then 88. So after the 10th iteration, as you can see, it became 93.64. And it even started from 81.85, which alone in itself is a much more better learning than the initial accuracy we had, which was 64 and 73 on the second try. And here you can see it's 81, starts from 81, and eventually goes up to 93.64, which is actually a really good learning. And it shows that the model has now performed better and more accurate. So overall, a quick recap on everything that was done. So for the first fix, what we did here is we reduced the learning rate from 8 down to 0.01, so the optimizer could update the weights in a controlled way. And for the second fix, what we did is we increased the network size from 4 neurons to a much larger capacity, so the model had enough room to learn. And for fix 3, what we did is we replaced the activation function from sigmoid to ReLU, which allows the gradients to flow properly during the training. And for fix 4, what we did is we reduced the batch size from 512 to 64, which gives the model more frequent and more accurate weight updates whenever there's a change. And for the last fix, we increased the epochs, or in other words, the number of times we iterate throughout the dataset from 2 times actually, to 10 times. So the model has enough time to fully learn from the dataset that it's given. So we went from 64% accuracy all the way up to 97%, or 93% actually. So I'm sure if we run it more, if we increase the epoch size, it will eventually get to 97% or even higher. So just by fixing these things, you can see that the learning of the model has become much more efficient and much more accurate. So this is the first things actually you need to check when the neural network isn't learning properly. Now, of course, there are also many more possibilities of fixes that we can make, and for larger models, there are different solutions, but for the baseline based models, these are the 5 most common fixes that we applied here. So if you found this helpful, make sure to like and subscribe for more practical AI tutorials. Or if you guys have any questions or any further ideas for other topics that you want me to explore, please make sure to let me know down in the comments below. Thank you for watching, and I'll see you guys in the next one.